All right. Hello, everyone. So this is the last lecture of the course. You made it, which is pretty cool. So I'm happy that there's a lot of familiar faces now. I think I know a fair number of people here, so that's awesome. Yeah, we all did it, which is great. There's just the small issue of the exam, but that's fine. So we had the mock exam. I collected the papers and marked them. So if you filled out the multiple choice things, those I gave you your mark for. And then the other questions, I just kind of wrote like comments about if the setup is correct, etc. If there is an arithmetic mistake, I noted that. So at the end of lecture today, if you did the mock, they're here. And you can pick up your mock exam either during the break or at the end of lecture. So yeah, so thank you for completing those. I have the sense that the exam will take about 2 hours and 45 minutes. So we've got 3 hours for the exam. So it's going to be kind of tight. There's a couple questions on the mock that were difficult, that were a little bit tricky. So I'm happy that people wrote the mock, because we were able to identify those, and I'll try and make the final exam less tricky based on the results here. One thing, I sent out an email this morning about question 6.4 on homework number 6. That question was just way too hard. It was one of these things that I wrote it down and I was like, yeah, that's reasonable, that'll work. And it's actually way harder than I thought. It's like a D-level course question. So that one's not going to get marked. So if you struggled with it, that's great. Struggle builds character. If you handed in your assignment, you had no idea how to do it, it's okay, that question won't get marked. Yeah, because it's too hard. Okay, so that email went out this morning. What are we up to now? Okay, got that. Change of coordinates. Okay. So our last lecture is going to be on change of coordinates. Okay. So this is a lot like what we do in one variable calculus where we perform a substitution when we're integrating. Change of coordinates is like substitution, but mechanically it's much more complicated than what happens in one variable. So we're going to sort of slowly build up to the idea for the next hour, and then we'll dive right into it in the second hour of lecture. Yes. Just for the people who are showing up, we have the mock finals, and you can pick them up during the break or at the end of lecture. Okay, so our first definition. We're just going to pay attention to what happens with linear transformations. Okay, a linear transformation is a function that takes a vector and outputs that vector times a matrix for some matrix A. Okay, and at the end of Tuesday's lecture, we briefly talked about the following. if the determinant of A is not 0, if it's not 0, then the function or the linear transformation is 1 to 1. And onto. So just as a reminder of what those words mean, something is 1 to 1 if whenever the outputs of the function agree, the inputs had to agree as well. Okay, so if we've got an invertible matrix, we've got AX is equal to AY. We can multiply by A inverse, and we get X is equal to Y. For onto, that means for all vectors B, there is some vector X such that AX is equal to B. Or here, we should say that in terms of our function. Okay, so what this is saying is if two vectors get sent to the same place, then they were the same vector to begin with. And this is saying for all values B, you can find a value that gets sent there. Okay, so that's what I was calling last lecture the fundamental theorem of linear algebra. And in mathematics, linear transformations are, in some deep sense, sort of the best transformations. They're the transformations that are easiest to work with, that have the nicest properties algebraically, etc. Okay. So a question from the textbook that I'd like to go over is, how do we use a linear transformation to move one thing so that it looks like another? So let's see. Okay, so let D star be the unit square. It'll be the unit box. Let and let D be the parallelogram with vertices these four vertices. Okay, so what we want to do is find a linear transformation that takes D star onto D. Okay, so we've got four vertices, we've got this square, and we're trying to map the square onto the parallelogram. So what would that look like? I only have two colors of chalk today, so it's going to be sort of a very Christmassy lecture. Okay, so here we've got D star. Okay, so there's our domain, D star. And we want to map it onto the domain D, which looks like this. Okay, so we're looking for the map that sends D star to D. Okay, so we have to so our unknown is a function. Okay, very good. So how do we go about doing this? Okay, we're going to give some name to that matrix, the matrix that affects this linear transformation. And you'll note that this guy, this matrix, when we multiply it by the vector in the x direction, gives AC. And gives BD. Okay, so we want to send 1, 0 to say this guy. So we get that if 1, 0 is going to this guy, then we should have the following thing. And if 0, 1 is going to this guy, then we'll have the following thing. So our matrix is the following matrix. Okay, so that is a linear transformation that'll take this green region here and transform it onto the red region there. Okay, very good. And if we check the determinant of this, we'll get the determinant is 6. So this means this is going to be 1-to-1 and onto. Okay, so our function's a pretty nice function. Before we go on, are there questions there about that algebra? Yes?
We have to check that, for example, it goes to -2, 0. The vector 1 goes to -2, 0.
Ah, yes, that's a clever thing, right? I told you where 2 of them go, but what about the third one, right? So yeah, that's a very clever thing to check. Okay, so we do the multiplication, and we get -2, 0. Yeah, so if this last vertex was like -100, 0, then there would be no linear map. Kind of not an obvious point, but the textbook writers, they made a linear map. So that's good. Yes, good, good, good. And I want to remind you of a fact from way back at the beginning of the course about determinants and areas. So if we've got this domain, and we've got this linear map, okay, we want to find the area of D and the area once we apply this map to D star. So what do we get? Okay, there's our region D star. And when we apply our function, that will distort the region D star a little bit. So this guy here will get sent to 0, and this guy here will get sent to 0, 3. So there's f of D star. And we see that there's been some change in area. So the area here will be 1, and the area over here will be 6. Okay, so when we apply this map, there's some kind of stretching that enlarges the area of our region. Okay, and I'm doing this example to remind you of the following fact from way back in the course, which is the determinant measures some kind of volume or area in the following sense. Okay, so if we take our unit cube, our unit square, or our unit cube, and we apply the transformation A, then that'll give us some region in space. It'll give us some, here we started with a square, and we wound up with a rectangle. If we measure the area or volume of that rectangle, that'll give us the determinant of this guy. So this area is equal to the determinant of our matrix. Okay. Yeah, so that's a very nice way of thinking of the determinant that we'll be using more and more in the rest of the lecture. Okay. Okay, so when we apply a linear transformation, areas get distorted. They get distorted according to the determinant. So how does this relate back to multivariable stuff? The connection is something called the Jacobian matrix. Given a function like this, we're going to write that we take two inputs, u and v, and we get two outputs, okay, x and y. So these x's and y's depend on u and v in some way. So it's also convenient to write this as x of uv, y of uv. Okay? Because both x and y will depend on u and v in some way in what follows. Okay, the Jacobian matrix is the following thing. Okay, so we're using our partial derivative symbol in a new way. The partial derivative of the coordinates x, y with respect to the coordinates u, v is the following guy. Okay, so it's the partial derivatives of all of the coordinates. Okay, we could also think of this as the total derivative of f. Right? This is also from earlier in the class. The total derivative of the change of coordinates. Okay, so that's a very helpful matrix to have kicking around. So I want to do one simple example of how this works. Okay, so if we've got a change of coordinates that's given to us by the following formula, so we plug in our values u and v, they output our new coordinates x and y. We want to find the Jacobian matrix of this guy. So we start off taking the x coordinate, we take its derivative in u. We get 2. We take its derivative in v. We get 3. Derivative in u. Derivative in v. Okay, so there's our Jacobian matrix. And there's sort of a nice fact. Okay, our coordinate transformation was given to us by a matrix. So if we have a linear change of coordinates, okay, if we have a linear change of coordinates, then the Jacobian matrix of that transformation will be the matrix of the transformation. So for linear things, the Jacobian and the matrix agree. Okay, so that's sometimes helpful to keep in mind. Okay, very good. So there's the Jacobian. Sweet. Okay, right. So now I'd like to get on to the change of coordinates formula. But before we get there, we should say a little bit about what this looks like in one variable. Okay, so in one variable, we've got the following thing. Okay. So in one variable, we have this idea that if you've got what we usually call a U substitution, that this should be equal to A, B, f of u du. Okay, if we can substitute a variable u and we have its derivative here, then we should be able to replace that domain with A and B. Okay, so that's our sort of the substitution formula. As it works in one variable calculus. Now I want to go on to what this looks like in multivariable calculus so that we can point out sort of the structural similarities. Okay, so suppose we've got a two-variable function. Oops. Okay, so suppose we've got a function which is 1-to-1, onto, and C1. Then we have the following change of coordinates formula. Okay, we can switch between coordinates in the following way. So what I want folks to notice here is the way that this kind of looks like there's cancellation. Okay, when we look at the one variable formula, right, we see that these guys sort of cancel off and become a du. Right, just like we'd expect, they should cancel and become a du. Here, the variable becomes a u on this side. Okay. Similarly, here, these guys should cancel off and become the dy dx that we have on the other side. Okay. So the cancellation, I find, helps me remember the shape of this formula. Okay. These inputs here are on both sides of the equation. They're called xy. And the cancellation gives us that there should be like a dx dy there. So we're going to spend the rest of the lecture sort of getting familiar with this multivariable version of things. Right. Okay. Dun-dun. Okay. So here's the kind of reason why, or here's an example of where we would use substitution and what it would get us. So when we draw this region R, we're going to get a parallelogram that looks something like this. Okay, and setting up an integral over this region would be pretty technical, right? We would need to make a couple splits in the region, and then the bounds would always be changing. So setting up an integral over this region itself would be quite difficult. So what we're going to do is we're going to use change of coordinates to get to a nicer region where the integral is easier to compute. And we don't have to set up all sorts of complicated bounds. Okay. So following with this example, we've got a Jacobian over there. Let's use it. So we're going to realize this parallelogram as the image of the unit square under a transformation. Okay, so we're going to think of this as being R star. Then we transform it according to this guy here. And we get this region here, R. Okay, so what we're going to do is use change of coordinates to, instead of integrating over R, which has all sorts of kind of corners and is tricky to set up, we're going to integrate over R star instead. Okay. Yeah, let's. Okay. Right. So when we start off with this guy here, we're going to apply change of coordinates. And the change of coordinates formula is going to tell us that we get the following thing. So now we have to work out what we'll get for x and y. Right, so we're using this linear transformation to go from coordinates u and v over here. Right, so these are uv coordinates over to our x, y coordinates over here. Okay. I'm usually quite picky about labeling axes, and this is one of the times when it pays off, because now we can make a distinction between the stuff going on in uv coordinates and the stuff going on in xy coordinates. All right, when we calculate this Jacobian, it's a linear transformation, so we've got the same matrix as the transformation matrix. And we get the following thing. And this guy, when we multiply it out, we get 4 minus 9. And we should note that there's an absolute value there. The absolute value is very important. Okay, so continuing on with the calculation, in UV coordinates we've got very nice bounds on our region. Right, there's no complications, there's no variables in the bounds. We just are integrating this guy all the way through. Okay, and now we can calculate this thing out using elementary techniques. So I'd recommend pulling the 5 out front and then multiplying this stuff out. So you'll get the following guy. Then we have to integrate in U first. These guys, I guess, will join together to make 11. Oh yeah, 13. Zzz. No coffee yet. Okay, so we get here. When we evaluate, this will become 2. We get here, and then this we can integrate just like in one variable. Okay, and then we have to evaluate this guy. And we've completely run out of space, as always. We get this guy. Okay, so we should get 145 quarters. Okay, sweet. So the purpose of doing this is so that we don't have to work over this original region with lots of corners and stuff. When we do change a variable, we can get somewhere that's nicer and easier to work with, and there are fewer corners. Are there any questions there, or any typos spotted? Yep.
Just a question. So how can we get the shear square conformation matrix 2332?
Oh, right. Yeah. Great. Yeah. Yeah. Where does that matrix come from? When we apply this, right. Sure. Yep. Good question. Right, so we want to go to a simpler region, right? We want to work on a simpler region, so we might as well work with the unit square. And we've seen that we can make the unit square into any parallelogram we want, right? We send this guy to one of the vectors, this guy to another vector. So we decided, okay, this guy will go here. This guy will go here. And to get that matrix, we do that same kind of yeah, okay, one sec. Okay, let's erase all this stuff. Okay, so in terms of picking the matrix, how do we get this matrix? Right? We're going to send 1, 0 to 2, 3. And we're going to send to 3, 2. And when we do that, when we choose that this guy goes here and this guy goes here, that tells us what the entries of the matrix should be. Very good. Yeah. Are there more questions or thoughts about where that matrix comes from, or how the change of variables goes? After the break, we're going to do a whole bunch more examples of this technique, so you'll get a feel for it. Okay. So let's take 10 minutes. If you wrote the mock midterm or mock final, please come and collect it. There's a couple of people who didn't put their names, so. If you wrote it, please come up and collect. And okay, very good. So clearly, change of variables has a lot of sort of technicalities and things going on with it. I want to show some more examples of how this technique works so that you're more familiar with it. So on the mock final, there was a question. Which was from the textbook. Which said the following thing. Okay. So we were supposed to evaluate an integral over a particular given region using the following change of coordinates. Okay, so it gives us the change of coordinates, but at the time of the mock final, we didn't have the tools to really use this. We didn't have this formula here. So now I want to go through this example using change of coordinates formula. So the first thing to do is to get a handle on the original region. Okay, so we're going to be bounded by x plus y is equal to 1, x plus y is equal to 4, and then we're going to be bounded by x is 0 and y is 0. So here's our region in the plane. Okay, so again, this is a complicated region. A couple of people managed to solve this question by breaking it up like this, and then doing one integral here and one integral here. We're going to show how to do it with change of coordinates so that we don't need to break up the region. We just need to be quite clever. Okay, so one of the hard things about change of coordinates is that we need to figure out the UV coordinates that get sent to these XY guys. Okay, so what in UV gets sent to those guys via the map U minus UV, UV. Right? We have to find the region that gets sent onto these guys. So one nice thing is that we can use these formulas here. Okay, we know that x is u minus uv, y is uv, so we get that along this edge of the thing, we are equal to 1. Okay, similarly, along this edge, u is equal to 4. Okay, so things look like that. And now we have to figure out what's going on these edges here, on these two guys. So if x is equal to 0, that tells us either u is 0 or 1 minus v is 0. Right? But we know that u is always going to be between 1 and 4. So our x plus y value is always going to be between 1 and 4. So we get that v must be 1. Okay? That's a pretty subtle argument. What we're arguing is x plus y. X plus y gives us our u coordinate. So down here, x plus y is 1, then it's 2, then it's 3, then it's 4. So anywhere in this region, u will be between 1 and 4. So we know that this u guy is never 0, so the v guy has to be equal to 1. Okay, so what that's saying is that our v will be equal to 1 here. All right, and then we get this product is 0. We have v does not equal to 0. Sorry, u does not equal to 0. Thus v is equal to 0. Okay, so under this change of coordinates, our region R star is this guy here. Okay, so this kind of rectangle gets sent onto this this shape here. Okay, so now we've set up our domain and our change of coordinates. Okay, so let's calculate the thing. Okay, so we'll apply change of coordinates, and we get the integral we want is the integral over r star u minus uv. So we plug in our values for x, we plug in our values for y. Now we put the Jacobian matrix here. So the Jacobian for this guy is 1 minus v, negative u, v, u. Okay, so we take the derivatives of the first coordinate in u, first coordinate in v, second coordinate in u, second coordinate in v. Okay, now the determinant here will be absolute value following guy. Right, one sec. Right, so we integrate this out, and we're going to get Right, so the algebra happens that this gives us a u. These guys cancel out. And now we're left looking at this thing here. One sec. Yeah, okay. So our bounds from our star are over here. So we go between 0 and 1 in the v-axis, and between 1 and 4 in the other axis. Okay, so we're ultimately calculating the area of this thing. So the thing should integrate out to 4 in the end. Right, so that'll be Sorry, we should integrate out to 3 in the end, which is the total area of that R star. Okay, so when we do our coordinate transformation, we're really just integrating 1 the whole time. Okay, questions there or thoughts there? Okay, sweet. Okay, so now I want to introduce a really different looking coordinate system, something that, here we're going between Euclidean and Euclidean. I want to introduce something that looks sort of fundamentally different and which might have useful applications down the line. Okay, and that's the topic of polar coordinates. Okay, so these are a system of coordinates completely different than the Euclidean ones. So we're used to drawing things like this, x and y. And we say, here's the line x equals a, here's the line y equals b, and we get to AB, and we call these our Euclidean coordinates. Okay, polar coordinates are where we do the following thing. Where we measure an angle theta and a distance r. Okay, so they're a completely different way of mapping points out on the plane. So this would be the point r theta. Okay, they're called polar coordinates because they're useful for calculating things like centered at the North Pole or centered at a particular rotational axis. Okay, Very good. So I'd like to graph a couple things in polar coordinates. Okay. So to plot points and to graph things in polar coordinates, we proceed much the same way as we would in Euclidean. We start off with sort of a game of connect the dots. So here we'll start off at 0, 0. And we care about measuring angles positively from that axis up. So when we get to here, we will reach the point pi by 2. When we get to here, we'll reach the point 2 pi pi, 3 pi by 2. So what this will look like is some kind of spiral that's coming out of the origin. Okay, we'll get a curve where as the angle gets bigger, the radius gets bigger. Okay, so we'll circle around like this, and the next time we meet this axis, we'll be at 5 pi by 2. Okay, so that's very nice. That's a nice curve. Okay, so how do we switch between Euclidean coordinates and polar coordinates? Okay, the idea is we draw a triangle and label it with the components we have. So if we've got a theta here and a length r here, we're going to get x is r cos theta and y is r sine theta. Okay, so to go from polar to Cartesian, we can use trigonometry to get our values there. Very good. Okay, and to convert the other way, right, we can calculate out what r is. Okay, so to figure out, given a Cartesian point, what are the polar coordinates, we can go the other way. Okay. Very good. So what would change of coordinates give us? Okay, if we've got an integral that we want to express as an integral in polar coordinates, we have to use change of variable, and we'll get the following thing. Okay, so we're looking for that, that Jacobian identity that will come up here. So we take these guys here, calculate our Jacobian matrix, okay. And when we calculate this out, we're going to get r cos squared plus r sine squared. So what we'll get right? We have r cos squared, r sine squared. We factor out the cos squared plus sine squared, and we get an r. So this Jacobian matrix is going to simplify down to an r, which produces, I think, the funniest joke in the whole course. What do pirates say when they get near the North Pole? Ardy theta. Yeah, so in polar coordinates, pirates say ardy theta. Very good. Okay, so there's the change of coordinates formula for polar. Okay, very good. Yeah. Okay. Okay, so I want to do a calculation where we really need polar coordinates, where polar coordinates kind of save the day. Okay, so integrate e to the x squared plus y squared over this disk, right? Quite hard to do because it's very hard to get an antiderivative for e to the x squared, right? So this e to the x squared will give us a lot of difficulties unless we switch coordinate systems. Okay, so to switch coordinate systems, we're going to write this r star as a region in polar coordinates. So we're going to switch over our variables to polar variables using these formulas. Okay, so we get r squared is less than 1, or equivalently, r is less than 1. Okay, so our unit disk is the set of places where r is smaller than 1. And now we'll apply this change of variables formula. Oh yeah, sorry, and we can say what cos should be, or what theta should be. We're going to go around the whole circle, and we only need to go once. So theta will be between 0 and 2 pi. Okay, and now when we apply change of variables, whoops. We put in our formulas for x and y. And then we have already computed the Jacobian up here, and it gives r d theta. And we get here. Okay, so the integral that we want to compute is 0 to 2 pi, 0 to 1, following guy. Okay, so to compute this thing in r, we note that the derivative of e r squared will be e r squared times 2r. Right? So we're going to do a little substitution. And we get here. Right, so when we take the derivative of this, the r squared will give us a 2r, which will cancel here. Okay, and then we get following thing. Oh yeah, sorry, we should have thetas there. Okay, and applying fundamental theorem of calculus. We get this. And our final answer is this guy. So pi e minus 1. A really beautiful number. Are there questions there or thoughts about that calculation? This is a really, really rapid introduction to polar coordinates. I hope that this calculation of the Jacobian comes in handy here. Okay, very good. Yes? Which theta to choose? Right, yeah, right, very good. Right, so we've got this disk, x squared plus y squared is less than or equal to 1, and we know this guy has radius r less than or equal to 1. So what we decide to do is to cover the whole disk once. So we start here. That takes us to pi. We keep going. That takes us to 2 pi. So the choice of 0 to 2 pi, right, is so that we cover the whole disk once. Does that help? Okay. Any other thoughts or questions about the setup there? Okay. Very good. So I think with this lovely number, we should leave it there and move on to summary. Yeah. Okay, so what did we see this week? What's the news of the week?
Polar coordinates.
Yeah, lots of polar coordinates really fast. Okay, we saw polar coordinates. What else? What did we see on Tuesday? Still, yeah? Yeah, onto and one-to-one. Okay, so key concepts, we saw change of variable, sort of a big technique. Jacobian Matrix. Okay, anything else? Any other thoughts? Techniques from the week? Okay, yeah, I think that's pretty accurate. We had a pretty short lecture on Tuesday. So, okay, so I see everyone's like, oh, let's go, let's roll. Okay, so there's a couple matters of business to do. So the first is we've got our exam, which is Friday, August 17th. The announcement I made in Tuesday's lecture, I had the wrong times. So I sent everyone an email about this, but I want to make sure that everyone knows the time is 9 a.m. to 12. Okay, so it's an early morning thing. I am not a morning person. I'm sure a lot of you guys are not morning people. But if you want to score as high as possible on the exam, I highly, highly recommend getting up at 9 a.m. a couple other days. You know, so don't sleep till noon, Monday, Tuesday, Wednesday, Thursday, and then expect it to go differently on Friday. So please make a point. So try and make a point of practicing getting up early. You know, set your alarm, get your neighbor to wake you up, it doesn't matter. Make sure that you wake up on time for the exam on Friday morning. People who arrive late won't be given extra time, and if you don't show up for the exam because you sleep in, you simply get 0. That's the whole story. Sleeping in is not a medical condition. We can't help. So how are people feeling given the mock exam? Are people feeling comfortable with the course? Uncomfortable? Okay, no one ever says that one. Anyway. So the best way to prepare for the exam, I believe, is to try the mock exam. If you haven't got it yet, the PDF is online. So the PDF is on the blog. I recommend downloading this, print off a couple copies, and just do them Wednesday and Thursday morning. You know, one of the aspects of university is that we have these kind of marathon exams. They're 3 hours long. So it takes a lot of, like, what should I say, attention and, you know, stamina to write a 3-hour long exam. So I highly recommend practicing for 3 hours early in the morning, just to get used to that kind of marathon writing. When we did the mock exam, there was only 2 people who stayed past 2 hours. So, you know, you got to practice this at some point. Yeah, okay, so there's that. What else? Oh, I'm going to have a day scheduled for handing things back. I'm not 100% sure what that day is yet. I think it's the Tuesday before the exam, but you'll get an email about this. So as you can see, there's these to hand back. There's still midterm remarks to hand back, and there's still deferred midterms to hand back. So if you want that paperwork, we'll be giving it back. Oh, also homework 6. You're handing in homework 6, and it is graded, but there's no tutorial next week. So you'll have to get it back during specially arranged office hours. I'll send an email out about when picking things up time is. Okay, so it's probably the Tuesday of this week, but I still have to figure out my schedule. Yeah.
Is that mark going to be posted online? Is that mark
yeah, I guess it should be, eh? Yeah, it should be. Yeah, good idea. Okay, are there any other questions or thoughts about exam stuff? Questions, ideas? Okay, well, ladies and gentlemen, this is the end of the course. You survived. I'm so thankful to have taught you. You're all brilliant people. Have a good one. Thanks a lot, folks. I'm sorry for all the typos.